In today's video, we are going to talk about transformers. And in transformers, we'll talk about power transferring mechanism and two types of transformer. That is what a step up and a step down transformer. So what happens in a step up transformer? It can increase the voltage and reduce the current. And what happens in a step down transformer? It can decrease the voltage and increase the current. So this is one of the best selling point of the AC over DC. AC current voltage can be changed. Okay, frequency will not be changed, but AC current voltage can be changed with the help of transformer. And why do we need all these changes? Because of transmission, there is a big loss in transmission lines. Okay, so what happens? We generate AC power at a power generating station, and this is to be sent to homes, houses, and houses are generally very far away from the generating stations. So I square losses, heating loss in transmission line will be high. To reduce this, what we need to do, we have to reduce the current. We have to reduce the current, and when we reduce the current, voltage is upped, voltage is increased. That process is called a stepping up. Okay, we are increasing the voltage. And at the for the end users, what happens? Voltage is again decreased and current is increased. Okay, so that is what happens. And then we are going to see the efficiency of a transformer. What are the problems? And one of the big problem will occur due to eddy current. Okay, and we will see how can we get rid of, how can we reduce the eddy current. Okay, and at the end we are going to study about skin effect. Okay, so let us start. How the transformer will look like? We will have transformer. So we have a soft iron core. I am not drawing a 3D picture. Okay, I am drawing a 2D picture. So this is not a plate, this is a limb. Okay, if you see the cross section here, if you see the cross section here, it will be rectangular cross section. Okay, here will be rectangular cross section, here also will be rectangular cross section. Okay, so I will write it here, rectangular cross section. It can be a square also, but a square is some kind of rectangle. Now this is a soft iron core. Soft iron core, it has high susceptibility, high permeability. Okay, so very high permeability. And what happens because of this high permeability? What we are going to do, we are going to apply a source of EMF. We call this primary winding. Okay, we call this primary winding. And there is a source of EMF. Okay, this source is sinusoidal, this is AC source. Okay, and this value is E1. E1 is sinusoidal. Okay, and because of this thing, what will happen? Because of this what I am assuming, this circuit has no resistance. What I am assuming, this circuit has no resistance, but still it has inductance, and because it has inductance, what will happen, some current will be flowing, okay, is. This is will be obviously changing its direction this way or this way, okay, depends on the phase, okay. But one thing is there, E1 and I1 will be completely at 90 degree, because this is a purely inductive circuit. So I will draw this, I will keep drawing this phase diagram also. So this is our E1, this is our E1, and I1 will be, Is will be like this, okay. We know this, in purely inductive in purely inductive circuit, what happens, current lags the voltage, current lags the voltage. So same thing is here, okay. I will draw it a bit bigger, okay. And because of this current, what will happen, some electric field lines will set up, and electric field lines will travel like this, electric field lines will travel like this, because it is a soft iron core of high permeability. What will happen, these electric field lines, sorry, these magnetic field lines will remain inside, this, okay, inside the soft iron core, okay. They will pass like this, okay. You can show as many you want. And now there will be a secondary winding, okay, there will be a secondary winding. Secondary winding, and I am not showing any load resistance here, and what I am saying, some EMF E2 will be induced here. This E2 will be, this E2 will also be sinusoidal in nature. And one more thing is there, whatever the magnetic field lines are there, they will go like this, and they will make closed circle, okay, closed path, okay. And what I am assuming, no magnetic field lines are going like this, okay, they are not going into the air because of this soft iron core of high permeability. So if the flux with the, if the flux linked with one of the turn is phi, here also one of the turn, it will be phi. But there is a difference. What is happening here, n1 is the number of turns, number of turns in primary winding, okay. I will just write pw, okay, primary winding, okay. And here n2 is number of turns, number of turns in secondary winding, okay, secondary winding. Clearly you can see that number of turns in primary winding is more than number of turns in secondary winding. So total flux linkage here will be phi primary will be phi primary will be n1 phi, and phi secondary will be n2 phi. You can clearly see that, here flux is less compared to this one, okay. Now the things are complete for now. We can find this EMF E1, okay. We can find this EMF in terms of these things n1 phi. How? We will apply the KVL, okay. We will apply Kirchhoff voltage law. So Kirchhoff voltage law, total voltage should be 0. So applied voltage is E1, and here it will be L di by dt, L dis by dt, or simply the this rate of change in flux, with a minus sign. So it will be N1 d phi by dt, it is 0. Okay, so what you got for E1, you got E1 for E1, N1 d phi by dt, N1 d phi by dt. Now what about E2? E2, here E2, Faraday's laws, we can find E2 using Faraday's law, and E2 will be minus N2 d phi by dt, that is rate of change in flux. Okay, that is what? Rate of change in flux. So what you see up to now, up to this point, what you see, E2 and E1 look same, there is a negative sign. Okay, so E2 by E1, E2, sorry, E1 by E2, E1 by E2 will be N2 by N1, sorry, N1 by N2, but with a negative sign. So up to this we have seen that E2 will be a smaller than E1, but opposite in phase. So I will show you E2 this way. I will show you E2 this way, and we are going to go in the next page. In the next page, I will draw one load resistance here. Okay, but before that, I want to discuss one more thing. See here what is happening. EMF is E1, this IS is out of phase with E1, not out of phase, 90 degree, 90 degree phase difference is there. Okay, so P primary is going to be 0. Okay, because of this phase angle. Okay, and P secondary is also 0. Why P secondary is 0? Because there is no current. Okay, so there is no power, but yeah, it is there is a current. Okay, there is a current, there is a flux going on. Sometimes magnetic field will go this way, sometimes this way. So but we are not getting anything, right? We are not getting any input, and we are not getting any output. But now we will apply one but now we are going to apply one resistance, load resistance, at the primary, in the secondary. So this is our inductor, sorry, transformer, and we have some primary winding. Okay, I will not write so many things here. Okay, so this is E1, and we have a secondary winding also. Number of windings here, number of turns here is less, and we have a load resistance R. Okay, and EMF induced here was E2. EMF induced here was E2, and there was a current here also, IS. This current can change direction. This is sinusoidal. Okay, this is alternating current. Everything is alternating. I have not shown the magnetic field, that is also alternating in nature, magnetic flux is also alternating in nature. Now what will happen when you apply a load resistance? What will happen? One current will one current will come into the existence. Before we going that, let us draw what we have already done. E1 and A2 were at opposite, right? And Is was at 90 degree with E1. And what I'm saying, this I2 will be okay, because because of this I2, one I1 will also generated here. This I1 is also sinusoidal. Okay, this can be positive, negative, any value. Okay, now what I did, I have one extra current I2 here, one extra current I1 here. But what I want to say, I2 will be in phase with E1. E2 and I2 will be in phase. Okay, because this is the resistance. Okay, because this is the resistance. Now because of this I2, one extra current I1 will come into the picture. Why I1 will come into the picture? This extra current will also will also create magnetic field, and this will change the flux, right? But here EMF is the same, source EMF is the same. So we want to keep the flux unchanged. So one extra current I1 will come here, and that I1 will oppose the I2. So what I want to say, I1 and I2 will be out of phase. Okay, now the things are complete. You can see that E1 and I1 are in phase, E2 and I2 are in phase, and Is is linked with this. Okay, but the angle is 90 degree. So what is happening? It will get power. It will get power from the source. Okay, but primary wire will get power from the source, but it will not use the power. Okay, it will deliver it to the secondary. Okay, and here the same power will be delivered. Okay, and power delivered here will be E2 I2. So basically this is the power delivered by the delivered by the source to the primary winding, and primary winding is not dissipating any power. Okay, power is dissipated in secondary wire. Okay, power is dissipated in secondary power. Okay, it is just taking and transferring. Primary is just taking from the source and transferring. Okay, it is still getting the power. Okay, so even this is also positive, this is also positive. Okay, so power in primary will be power in secondary. So this will be E1 I1 and E2 I2. They will be both equal. So I1 by I2 ratio, we can find I1 by I2 will be E2 by E1, that is minus N2 by N1. Because N2 is smaller, in our particular case N2 is smaller than N1, what we see, voltage is increased but current is reduced. And what is happening? Power will remain same. Okay, so let us summarize again. Let us summarize again. Let us say R is not there. This is the source EMF. This is constant. Okay, RMS value is constant. Okay, it is changing sinusoidally, but RMS value is constant. Okay, so this is producing some magnetic field, and because of this, E2 is coming in the picture. Because of this, E2 is coming in the picture, and that E2 is out of phase with E1. And this the reason behind this magnetic field is one current Is. S doesn't mean secondary. Okay, and this is the current in the inductive circuit, purely inductive circuit. Okay, now what we did, we just put the resistance R here. Because of this R, I2 comes in the picture, and as soon as I2 is coming in the picture, I1 is also coming into the picture. And what is the purpose of I1 coming into the picture? It will keep the flux same. So it is keeping the flux same. That means I1 and I2 are opposing in nature. Okay, I1 and I2 are in opposite phase, opposite phase, and E2 and I2 are in phase because I2 is due to this resistance. Okay, so E2 and I2 are in phase, and one current is coming into the picture, I2, and to oppose this I2, I1 is coming into the picture. Because they are opposing, the phase angle is different. So in this way, this thing is complete. And now what we see here, if you see, this is the input power. Okay, so efficiency is what? P output by P input. So P output is E2 I2 and P input is E1 I1. Okay, okay, so if you see this thing, it will come 1, but it is not 1. What is the reason? Efficiency is not never 1. Okay, so what is the reason? The reasons are different. Here, this circuit cannot be purely inductive. Okay, this will have some resistance. Okay, we can reduce the resistance, we can use thick wires. Okay, we can reduce the resistance, but it cannot be completely zero. Apart from that, what will happen, this flux is coming into the picture, but this flux is changing. The flux is changing, and because there is a change in flux, there will be eddy current, and those eddy current opposing will be opposing the original flux. Eddy current will also produce the magnetic flux, but they will be opposing in nature. So basically, you are trying to produce some flux, right? But you are getting less than that, less flux than that. Then someone is stealing your energy. This eddy current is stealing the, cancelling out some part of the flux. Okay, and it is stealing the energy, but where is this energy going? Eddy current is going to have some heating effect. Okay, and what we don't want the we don't want our transformer to heat up, so we have to take care of the eddy current. But for now, so because of this eddy current, efficiency will be less than 100%. Okay, and because of this inductive, this will have some resistance, this wire will also have some resistance. Okay, there will be some okay, there will be some loss. So right now our focus will be in AD current. We are going to focus on AD current. So for AD current, I will go to the next slide, and for this I will add one picture. Okay, from the from the from my collections. Okay, because sometimes it is what happened. So I am going to add this picture. Okay. So you can see the transformer limbs here, and here is the cross section. We are seeing cross section here. Okay, and a magnetic field is going into, and because of this magnetic field we are getting some AD current. Okay, suppose this magnetic field is, in this case, yeah, in this case magnetic field is increasing. So magnetic field lines are into the plane, they are increasing. So we should no, they are decreasing. Okay, so we are getting this kind of AD current. I will explain again. Magnetic field lines are going into, okay, and because they are decreasing, what will happen, some AD current is coming into the picture, and they will try to increase the flux. Okay, so how to increase the flux? They will create the magnetic field in the same line. Okay, so basically what is happening, they are opposing the changes, and this way these currents will create heating effect. This kind of heating effect happens in induction cooktop also. Okay, we use induction cooktop. So to reduce this induction current, what we do, we make many laminar, okay, laminated core. Okay, and the we are cutting, okay, we are cutting a small plate type things are there. Okay, and they are sticking together with a varnish. That varnish is insulating in nature. Okay, so this section is insulated from this section. Here you can see four laminated core, they are insulated from each other, which reduces the which reduces this area. Okay, overall, and when the path length is reduced, AD current loss due to AD current will also reduce. Okay, and because using this, what we can have, we can achieve high efficiency of the transformer. Okay, usually efficiency of the transformer will be greater than usually it will be greater than 90%. Okay, and if we have large transformer, then this kind of thing is okay, we can use uh, a very large number of seat, and efficiency can go close to 99%. Okay, for large setups. Okay, so this way we can get rid of AD current. Okay, and we have to talk about transmission losses also. This is not the part of transformer, okay. We are not talking about the losses in transformer, we are talking the loss in transmission line. So what happens in transmission line? Let us say we have a generating station, okay. This generating station, this is the generating station, and this is giving us current, and this current is let us say this current has voltage 1000 volt, okay, and the voltage is this much, and current is let us say current is very high. Current is also current is 10,000. So you can see that power will be 10 to the power 7 watt, okay, 10 megawatt power, okay. 10 megawatt is still a small, so this is a small generating station, okay. So what we are going to do, we are going to feed it in transformer, okay, in transformer, and we are going to increase the voltage, we are going to increase the voltage. Let us say this voltage is less, okay, let us say this voltage is 100 only, okay. So and so power is 10 to the power 6 watt, 1 megawatt, okay. So now what will we do, we will increase this voltage, and we will increase it by 1000 times, okay. So I am making it this much volt, and the current is reduced to, and the current is reduced to uh, current is reduced by 1000 factor. Now this current is only 10 ampere, okay. Now this is the transmission line. This transmission line is usually very long, okay. This transmission line is what, usually very long, okay. Now this is a very high voltage, okay, this can be dangerous, okay. Current is going this way, current is coming this way, current is going this way, current is going this way, okay. And the things can be different also, current may go this way and return this way, okay. So one path is for going, other path is for coming, and here we have a transformer, and here it is a step down, okay. Here we have a transformer, and here voltage will be reduced and current will be increased. So let us say this voltage will be 200 volt, okay, and current will be 20,000 ampere, okay. This is ampere, okay. Now this 20,000 ampere, it is a big current, but it is not for one home or house, okay. There are so many houses, okay. So what will happen here, this suppose this transmission line has a resistance R is 10 ohm. So power lost will be 10 square into 10, 1000 watt, okay. 1000 watt is the lost power out of 1 megawatt. 1000 so out of 1 megawatt, 1000 watt is lost, okay. These are all I mean I am giving this figure, these are not real figures, okay. These are good for calculation, okay. So so what is happening here, voltage is very high, transmission line voltage is very high, it is dangerous. Okay, if you go close to without touching, you can get the electric shock. Okay, electric shock. Suppose you have two things. Suppose two wires are there and there is a high potential difference between them. Okay, if they are very close, electric field between them can be very high, and because of this high electric field there can be electric breakdown. And what can happen, there can be a spark. Okay, air will can be ionized. Okay, so high voltage is dangerous. Okay, in our home we use the voltage of 240 volt, and our some power appliances still use a smaller voltage. For example, our mobile phones, they use 5 ampere, 10 ampere, 5 volt, 12 volt. Okay, and this kind of current they are using. So the voltage is again a step down by using the adapter. In adapter there is a transformer also that reduces the that reduces the voltage. Apart from reducing voltage, that adapter also convert AC into DC. That part we will study in electronics. Okay, basic electronics. Okay, so for now this is there, and we talked about a stepping up, a stepping down. So a step up transformer, a step up transformer, what will happen in a step up transformer? N2 will be greater than N1, so E2 will be greater than E1, but current will be less. Current I2 will be less than I1. And what about a step down? A step down, in a step down transformer, N2 will be less than N1, E2 will be less than E1, but current will be higher. Okay, so that is what we do. So I will finish this lecture here. Okay, that skin effect part is left, but I want to finish it now. Okay, bye.